Hello everyone, my name is Kyle Mummy, and today I'll be discussing the performance of my automatic lane detection system that I made for my remote sensing class at the University of Maryland. So in order to achieve this, I followed the following procedure. I uploaded a video file of a car driving down a road and broke it down frame by frame. Then, within the snip image function, I snipped that frame down to the region of interest. So in my case, I wanted to remove any potential sources of noise from over the horizon, such as trees or the sky, so therefore the top half of each frame was removed. Within the mask image function, a polygonal mask can then be added to the snipped region to block out any objects immediately outside the bounds of the lane lines, such as cars or barriers. Then, within the thresh image function, the mask region is set to grayscale so that I could set lower and upper bounds for the pixel intensity in order to create a binary black and white image. In order to adapt to different lighting conditions, the lower bound changes with each frame iteration. This is done by taking the mean pixel intensity of the masked area and scaling it. And this can be seen right here where my cursor is. So this image would then be taken and blurred to get rid of any white pixels that are noise and not actually part of the lane line itself. And this is done within the blur image function with use of cv2.gaussian blur function. So next, within the edge image function, the cv2.canny function was used to create the edges of the lane lines. This is done by taking the derivative of the pixel intensity and defining an edge as a sharp change from pixel to pixel. In order to begin the overlaying process of the lane lines, the Hoff-lines function was used to define lines from the edges that were created. I defined a line as 30 consecutive linear points on an edge, and anything that meets this criteria will result in the function outputting a distance rho from the origin and an angle theta that is perpendicular to the line. So in order to differentiate between right and left lane lines, I created two functions, left line stats and right line stats, which set the lower and upper bounds for the angles at which each lane line would typically be oriented when driving down the road. Specifically for the left lane, I set any line that has an angle from 30 to 70 degrees to be within the typical range of the angle that a left lane line would make as it approaches the horizon line. This range is relatively large to account for transitions between lanes in which the angle approaches 90 degrees. So any line that fits into these angular bounds from the cv2.Hoff-lines function will be accounted for within the left lane line. And these rho and theta values will be assigned to arrays specific to the left lane. So from there, the median thetas and rhos for the left lane will be calculated by using the numpy median function. There, it will be used to be input into the geometric equations that will determine the starting and end points for the left lane line. And this is critical because these points will then be input into the cv2.line function, which will be used to plot the lines within the main. The endpoints will then be trimmed down so that they can only span the region directly in front of the driver's point of view, which begins at the front of the hood and ends before the horizon line. Since the camera is located in a fixed position, I set the min and max Y values in the main, which are inputs to the left lane lines stats and right lane stats functions. The slope between the original endpoints is taken, and the new X points are generated using point slope form. These Y values are then redefined to equal the min and max heights that are set in the main, and the 4 coordinates that define the left lane are returned along with the slope, median angle, and median rho. So a very similar process is followed within the right lane stats function, except with the minimum and maximum theta bounds being changed to 110 to 150 degrees from the bottom of the frame. So now moving on to the main. So within the main, the video is taken in frame by frame. The minimum and maximum line bounds are defined, And the frame undergoes the process that I just discussed by sequentially calling the functions and applying each to the previously modified image. And this can be seen right here where my cursor is. So then both lane lines, starting and ending points, are obtained by calling the appropriate index of the right lane stats and left lane stats functions. These are then inserted into the cb2 dot line functions, which results in the left lane showing up in red and the right in blue on the screen. So now I'll demonstrate this automatic lane detection system on a video taken on a cloudy day with dark pavement. All right. So that gives you a taste of some of the videos that this code can output, where it shows the masked image, the thresholded image, and the image of interest, which is the original one with the new lines overlaid. So now I'll give you a look at a video that was taken on a much brighter day with tan pavement and see how this code reacts. All right. So as you can see, both videos feature some noise about the true lane lines, but the one in the brighter setting is much worse. This is due to the lack of contrast between the pavement and the white lines, which is a function of the pavement color and the glare from the sun. Also, another notable issue is that the code works noticeably better when tracking a solid line versus a dashed line. The negative space generated between dashes causes the line to jump in and out, while a continuous lane line is tracked more smoothly. So there's definitely some room for improvement from both a software and hardware standpoint. In the future, this code could be modified to create an array of all the endpoints that are generated in order to implement a moving average. This could substantially cut down on the noise and the fluctuation of the overlaid lines. In terms of the hardware, using a camera that could automatically adjust to the brightness of the environment could lead to a lot more consistency and versatility down the road. That's everything for now. Thanks for watching.